This is Unit 7, Physical Behavior of Matter. Lesson 4, Calculating Heat of Phase Changes. How is heat calculated during phase changes? The objectives of this lesson: I can determine the effect of IMFs on the heat of fusion and vaporization of a substance. I can calculate the heat required by a substance to go through a phase change, and I can determine the changes in energy of a substance. Do now. So when can you use Q is equal to mc delta T? You can only use this equation on the solid, liquid, and gas lines only. Used only twice. So that's important. So solid, liquid, gas. You can only use mc delta T there. So we did that formula before. That's where you have a temperature change. So whenever you have a temperature change is when you can use Q equals mc delta T. When we're on one of our solid lines, either liquid solid or gas liquid, we have two other equations we have to use. So the first one is our heat of fusion. This is the heat needed to change a substance from solid to liquid or from liquid to solid. The physical constants for water have that heat of fusion. For water, our heat of fusion occurs at 0 degrees Celsius. So you can add that into your reference table to help you remember that. When we use the heat of fusion, when we're at this liquid solid equilibrium, we're going to use Q is equal to mH sub F, which is on table F. So if you look on table F, you'll see that this is one of those three choices in the heat, calculating heat. So make sure you know where you can find that. An example of how to use this equation: how much heat in joules is needed to melt ice at 0 degrees if the sample weighs 255 grams. So here we have 0 degrees Celsius and melts. So those are your keywords to tell you to use. Q is equal to mH sub F. If we're looking for Q, that's our unknown. We have our mass here. They gave us the mass. It's 255 grams. And then we're going to plug in the number H sub F because we're at 0 degrees Celsius and we're melting. That's our heat of fusion right up here, 334 joules per gram. So 334 joules per gram. Then you'll see my grams cancel out. And then if we just take a calculator and just plug that number in, 255 times 334, we're going to get Q is equal to 85,170 joules. All right, the heat of vaporization, in contrast, is the heat needed to change a substance from a liquid to a gas or to a gas to a liquid. And the physical constants for water has the heat of vaporization for water. And so when water vaporizes or boils, that's at 100 degrees Celsius. So you can add that into your reference table right there. And so that's when we're going to use this formula up here, when we're going from gas to a liquid or a liquid to a gas. And on table T, you'll see that formula is very similar to our heat of fusion, except it's H sub V instead of H sub F. So notice those details. So an example of using the heat of vaporization: calculate the number of kilojoules. So notice the word kilojoules of energy needed to vaporize. That's a key word. Here's our mass of H2O. That's our substance at 100 degrees Celsius. So also a key phrase there. So when I have this vaporize and this 100 degrees Celsius, either together or individually, we know we need to use Q is equal to mH sub V. So Q is what we're looking for. The mass is 423 grams. And now we have to use, instead of 334, we're going to use 2260 because we're at the heat of vaporization. So we're going to use 2260 joules per gram. Our grams cancel out. So 423 times 2260 is equal to, our Q is equal to 955,980 joules. So they wanted it in kilojoules. So if you recall, using your reference table, if I'm going from joules to kilojoules, I'm going to move my decimal place 3 places to the left. 3 places to the left. So 1, 2, 3. So I actually have, I'm just going to round it to 956 kilojoules. So the effect of IMFs on H sub F and H sub V. So we talked about this when we did bonding. If the IMF is strong, the heat of vaporization and fusion is high. That means we have a high melting or boiling point. So this is a direct correlation. So as my IMFs increase, the heat of fusions and the heat of vaporizations, the boiling points and melting points increase. So here's another example. I'd like for you to try this. I will go over it in class. This is a heat of fusion example. And then here's a heat of vaporization example. They're in your notes, so I'd like you to try it, but I'll go over it in case you have trouble. And now a heating curve. I talked about these before, so what I'd like for you to do is use this and what we did before to fill in your heating curves on your notes in as much detail as you can. Make sure you have endothermic here. Make sure you're adding your different formulas. Make sure you add the temperature increases. In the vertical parts, that means average kinetic energy increases, and then potential energy remains the same. When we have plateaus, the temperature remains the same, and that means our average kinetic energy remains the same. And when we have our kinetic energy remaining the same, our potential energy increases. So notice that they're in opposites, except they never go down. When I'm heating it up, my potential energy and my kinetic energy increase. They just don't occur at the same time. So when I have a temperature increase, I have a kinetic energy increase. And when I have temperature remaining the same, I have potential energy increasing. I'll go over that again in class. Cooling curves are just the opposite. They're exothermic, so heat is being removed. So when I have the vertical parts, when I have temperature decreasing, my average kinetic energy is decreasing, and at those points I have potential energy remaining the same. On the horizontal parts of the plateaus, the temperature is remaining the same, and the average kinetic energy remains the same. However, the potential energy is decreasing. So stop and think. Okay, stop and think again. And then a quick reminder. So remember the 3 P's. If I have a plateau, I have a phase change, and that means potential energy changes. The diagonals mean that temperature is changing, therefore kinetic energy is changing. So check your understanding. Double check that you understand these concepts. And now you can determine the effect of IMFs on the heat of fusion and vaporization of a substance, and you can calculate the heat required by a substance to go through a phase change, and you can determine the changes in energy of a substance.